Hi, I'm Stevie Toll, and I'm covering motion and energy. Let me introduce to you my partner in crime, John Paul, the science guy.
John Paul, the science guy.
In physics, motion means a continuous change in the position of a body relative to a reference point, as measured by a particular observer in a particular frame of reference. Until the end of the 19th century, Isaac Newton's laws of motion, which he posited as axioms or postulates in his famous Principia, were the basis of what has since become known as classical physics. Calculations of trajectories and forces of bodies in motion based on Newtonian or classical physics were very successful until physicists began to be able to measure and observe very fast physical phenomena.
At very high speeds, the equation of classical physics were not able to calculate accurate values. To address this problem, the ideas of Henry Poincare and Albert Einstein, considering the fundamental formula of motions, were adopted in lieu of Newton's. Whereas Newton's laws of motion assumed absolute values of space and time, the equations of motion, the model of Einstein and Poincare, now called the special theory of relativity, assumed values of these concepts with arbitrary 0 points. Because, for example, the special relativity equations yield accurate results at very high and time. These concepts are prior to motion, just as the concept of motion itself is prior to force. In other words,
wait up. You want some breakfast?
Oh, sure. Sorry, we didn't have breakfast today.
I love the waffles. In other words, the properties of space and time determine the nature of motion, and the properties of motion, in turn, determine the nature of force. In the special relativistic model, motion can be thought of as something like an angle between space direction and the time direction. The special relativity in Newton's did not. The special relativity model is now accepted as explaining bodies in motion when we ignore gravity. However, as a practical matter, Newton's equations are much easier to work than those of special relativity and therefore are most often used in applied physics and engineering. In the Newtonian model, because motion is defined as proportion of space to Euclidean space, only relative motion can be measured, and absolute motion is meaningless.
An object is in motion when its distance from another object is changing. Whatever the object is moving or not depends on your point of view. For example, a woman riding a bus is not moving in relation to the seat she is sitting on. Do some wacky experiments. See, all you need is 2 bottles like this. You could have any type of bottle. And tape. You fill one of the bottles up with water in a pool, or just even a pitcher, it doesn't matter. And then you get the other bottle that's empty, and you stack it on the bottle filled with water. As you're doing that, you get the tape and you wrap it around. See, and after it's look like this. See, right now it's kinetic energy going to potential, but that's not the experiment. You see the water right here, it's a perfect example of potential energy because the water is sitting there doing nothing. When I grab it and use motion and energy, it should change into kinetic, making a tornado. I'll stand up for this one. As you can see, the tornado's right there. So this was John's wacky, cool experiment. See you later. Kinetic energy is energy of motion. A rubber band flying through the air has kinetic energy. When you are walking or running, your body is exhibiting kinetic energy. Potential energy is converted into kinetic energy. Before a yo-yo begins to fall, it has stored energy due to the position. At the top, it has its maximum potential energy. As it starts to fall, the potential energy begins to change into kinetic energy. At the bottom, its potential energy has been converted into kinetic energy, so that it now has its maximum of kinetic energy. For example, Stevie Toll will show you an example of potential energy stored to kinetic energy. Hello, Stevie.
Thank you, John Paul. This is an example of potential energy. Take a rubber band, for example, and you pull it back all the way. Now, that's potential energy. Now, if you take that rubber band and fire it, That's kinetic energy. Kinetic energy. At the bottom, it's potential energy. It has to get convert.
You messed it up.
I didn't know what to read.
I pointed to it right there.
It's recording.
No, it's not. Oh.
A waterfall has both potential and kinetic energy. The water at the top of brittle falls has stored potential energy. When the water begins to fall, its potential energy is changing to kinetic energy. This change in energy also happens at Niagara Falls, where it is used to provide electricity through the transformation of mechanical and electromagnetic energy to parts of the northeastern United States.
You idiot, I was telling you to do this. See? This. Is it that hard to do a signal? Look, I'm telling him to do this and he's not getting it.
It's recording.
Exhibiting, right?
Yeah.
No, and then I'm going to be like, see, I'll show you an example of kinetic energy. And then I'm going to grab the camera and it's going to show you like sprinting down the hallway, okay?
Mm-mm.
Why not?
This kinetic energy, well, this one, the cars that you pull back and let go.
Yeah.
And bring one of those. This is potential energy.
Ask
It's
it.
kinetic.
Ask Miss Krekler if she has anything that in her room that'd be example of kinetic energy.
I've got it.
Come on, slowly.
It's not.
What's that?
Oh shit, it's recording.
Oh. But when I pick it up and I put some energy in it, the potential will change into kinetic. See, look. As you can see here, we're making a tornado. A really crappy tornado. I'm glad you enjoyed our show today. As you can see, I'm going to take a refreshing swim in my pool. See ya!